The concept of logical equivalence is used frequently in this course. Let's examine this concept in more detail. First, let's introduce some notation and some preliminary concepts. Let's use a colon to mean has the value when giving names to non-numerical values. For example, the following line gives the name P to a numerical inequality. P names the proposition 3 is greater than or equal to 1 and less than or equal to 5. P is a true proposition. Similarly, the following lines gives the name P of X to an algebraic inequality. So P of X is the name of X is greater than or equal to 1 and less than or equal to 5. Now, P of X is not a proposition. A value of X must be chosen for P of X to become a proposition. For example, P of 2 is true, but P of 7 is not. P of X is a logical function. Put in a number X and get out a truth value. There's two other ways to make P of X into a proposition. This is where we introduce quantifiers. The quantifier symbol backwards E means there exists at least one. The quantifier can be used to produce the following proposition. Here's how to read this expression. There exists an X such that P of X is true. We usually assume that stating P of X includes the claim that it's true. So in detail, the backwards E means there's at least one. The X is a number X. The vertical bar means such that. And the P of X is X is greater than or equal to 1 and less than or equal to 5. This is true. There is such an X. The second quantifier symbol, upside down A, means for every. It can be used to produce the proposition that follows. And here's how you read this. For every number X, it is true that X is greater than or equal to 1 and less than or equal to 5. Now this is false because the claim is this inequality is true for all choices of X, and we have a counterexample immediately. We can choose 7 and it's not true. Logical implication is a relationship between two propositions. It's the foundation of logical equivalence, which we're on our way to exploring. One proposition in a logical implication is the condition, and the other is a consequence. When the condition is true, the consequence is guaranteed to also be true by the implication. So a logical implication is a kind of guarantee. If P is the name of the condition and Q is the name of the consequence, then an implication is written P right arrow Q. You can read this as P implies Q, P guarantees the truth of Q, and various other English expressions. Often it's read if P then Q, but in English, if and then constructions can mean many different things. The only way that this claim that P implies Q or P guarantees the truth of Q can fail to be true is if P is true, but Q is false. The following table shows all the possibilities. So for the condition and the consequence, P and Q could take on any values. And the first row, where P is true and Q is true, is reasonable because the truth of P in that case does guarantee the truth of Q. However, in the second row, in the case in which P is true and Q is false, P didn't guarantee the truth of Q, so that in that case, the guarantee would be false. The third and fourth rows are harder to understand. They're part of the definition of what we mean by this relationship. Let's say that they both occur when P is false, the condition is false. And it doesn't matter then whether Q is true or false. The guarantee P implies Q is true. The textbook has more detail that tries to motivate this definition. The guarantee is the foundation of logical equivalence. If P guarantees the truth of Q, so that P implies Q is true, and Q guarantees the truth of P, so that Q implies P is true, then we say that P and Q are logically equivalent. Logically equivalent propositions are either both true or both false. Here's a table that shows all the possibilities. So we have all four possibilities for combinations of P and Q. And if we look at the first row, well, when P is true and Q is true, both implications are true, and the equivalence is true. Now, in the second row, if P is true and Q is false, then P implies Q is false. And although Q implies P, the second implication is true, according to the table on the previous slide. Logical equivalence requires that both of these implications be true, and that's not the case in the second row. Similarly, on the third row, P does imply Q, according to the table in the previous slide, so P implies Q is true because P is false. On the other hand, Q implies P is not true because that's the case when the condition Q does not guarantee the truth of P. So the second implication, Q implies P is false in the third row. So in both those cases, second and third rows, the equivalence is false. On the other hand, on the fourth row, when both of them are false, P implies Q, according to the table on the previous page, that's true, and Q implies P is also true. So this table shows that logical equivalence means P and Q are either both true or both false. Here's a symbol for logical equivalence, P right left arrow Q. Logical equivalence between two propositions acts like numerical equivalence between numerical expressions. Because of this, it is given a second symbol, 3 vertical bars. This means the same thing. P implies Q and Q implies P. They have the same truth values. Here's a proposition involving quantifiers and an implication. You can read this. For every x, it is true that P of x implies Q of x. This is equivalent to choosing, or if we wanted to prove that this was true, it'd be equivalent. We can start by choosing an arbitrary or typical value, x sub a, and writing P of x of a implies Q of x of a. If it's true for every x, then it's certainly true for this particular one. For example, let's consider the proposition for every x in the real numbers, 2x plus 4 equals 8 implies 2x equals 4. You can see what's going on here is that you can see that you're subtracting 4 from both sides of the equation on the left, and that's going to give you the equation on the right. But we want to explore how this works with the quantifiers and the implication. This is equivalent to choosing an arbitrary value x sub a and writing 2 times x sub a plus 4 equals 8 implies 2xa equals 4. Well, since we're dealing with concrete values here, we can prove that this is true by assuming by proving that the consequence cannot be false when the condition is true. Suppose that 2xa plus 4 equals 8 is true. Then we can subtract 4 from both sides to see that 2xa equals 4 is also true. Once we know that the implication is true for arbitrary values, we know it's true for every value because we've only used properties of x sub a that are true of every real number. This means that the original proposition for every x in the real numbers, 2x plus 4 equals 8, does imply 2x equals 4. We can also show, using the same means, that 2x equals 4 implies 2x plus 4 equals 8 in the same way. Therefore, we know that these are logically equivalent. These two expressions, 2x equals 4 and 2x plus 4 equals 8. We're going to use this as a basis for looking at the solution sets of equations. This is a prelude to a topic in Chapter 1. So this is a foundation for a topic in Chapter 1. Solution sets and logical equivalence. The solution set S1 of 2x plus 4 equals 8 is the set of values S1 equals the set of all values, the set of all real numbers such that that equation is true. The solution set of the second equation, S2, is the set of all real numbers such that the second equation is true. These two sets are the same if they have the same elements. For this to be true, all the elements in S1 must also be in S2. That's for every possible element. If E is in set 1, that should imply or guarantee that E is in set 2. This implication has the symbolic notation or form or definition, S1 is a subset of S2. So the statement for every E member of S1 implies E member of S2. That's a definition of what S1 subset S2 means. We read that as S1 is a subset of S2. Also, S2 cannot have any extra elements in order for the two sets to be equal. That is, all the elements in set 2 must also be in set 1. And that's symbolically the claim S2 is a subset or inside S1. This S1 equals S2, the fact that both sets have the same numbers, makes the same claim as S1 is a subset of S2 and S2 is a subset of S1. So here we're repeating the two definitions of the subsets S1 and S2. We have seen that the two sets S1 and S2 are going to be equal if the following two implications are true. Because E is a member of S1 is true exactly when 2E plus 4 equals 8 is true, and E2, member of S2, is true exactly when 2 equals 4 is true, then S1 equals S2 is true exactly when the equivalence we showed a few slides back is true. In words, two sets are the same, are equal, that is, have the same elements, when the propositions or equations which define those sets are logically equivalent. As I mentioned earlier, this fact is used in the proof of the first theorem in chapter 1.